let's go over a few questions which are based upon what you learned earlier. This one says 5 separate figures, 1, 2, 3, 4. Are there 5? Sorry, there are only 4. Okay, so 4 figures involve a cylindrical magnet and a tiny light bulb connected to the ends of a loop of copper wire. These figures are to be used in the following question. The plane of the wire loop is perpendicular to the reference axis. The states of motion of the magnet and of the loop are indicated. The speed will be represented by V, and CCW means counterclockwise. So for example, in this case, in the first case, the magnet is moving away from this coil. Here is the coil and this is the light bulb which has some resistance, so it will light up because of the power dissipation I square times R. We are assuming it's an ohmic material. So the thing is, this magnet is moving away, this coil is stationary. In this case, the magnet is stationary, the coil is collapsing, it's crunching, you know. In the third case, the magnet is stationary, the coil is just being rotated in the counterclockwise direction. In this case, the magnet is stationary, the coil is moving closer to it. The question is asking in which of the above cases the light bulb will light up. You have 1 minute, please talk to a person next to you. All right, folks, the correct answer here is C, because in all of those cases, you know, in 1, 2, and 4, those cases, you can see that the flux through the loop is changing the time. In this case, the magnet is moving farther away from this coil, so the flux that is due to this magnet, remember the North Pole, for example, have magnetic field lines going out of them like this. So that flux is actually decreasing because the magnet is moving away. In this case, the coil is collapsing, so the area is getting smaller and smaller, and so flux is changing because of the area. In this case, again, the flux is increasing this time because the coil itself is moving towards the magnet even though the magnet is stationary. On the other hand, in this case, if you rotate something just in its own place like this, and its distance from this magnet is not changing, the flux is not changing, right? Does that make sense? So in those 3 cases, remember Faraday's law says that the flux, first of all, the rate of change of flux d phi over dt with time, and let's say put a minus sign, should be the induced EMF, right? And the thing is, and if there are n turns, of course, you will put n d phi over dt. What is the flux? Flux is basically integral B dA times cosine theta, and if B magnitude is constant and theta is the same, theta is the same everywhere over the area, you can pull the B out, you can pull the cosine theta out, and the flux simplifies to just B A cosine theta. This is because B and cosine theta can be pulled out, and integral dA just becomes the total area, right? Does it make sense? So this is the flux. So you can see that the flux depends upon 3 things. You can change the magnetic field to change the flux, you can change the area to change the flux, or you can change the angle between the magnetic field and the area vector to change the flux. So, and in here you can see in 2 of these cases the magnetic field is changing. In this case and that first case, because this thing is getting closer or that magnet is moving away. In the middle case, the area is changing. You could also have changed the angle by say, for example, tilting this thing like this, the coil. In that case also you would have seen an induced EMF, right? Does that make sense? Okay, so those are the different things that you need to understand about Faraday's law. Let's move on to the next question. Okay, so here it says a very long straight wire carries a large steady current. Rectangular metal loops in the same plane of the wire move with velocity v in the direction shown, which loop will have the induced current. So there are three cases. This is case 1. Here the loop is moving this way. In case 2, the loop is moving this way, and in case 3 here, the loop is moving parallel to the wire. You have 1 minute to answer this question. Your time starts now. All right, 7 seconds, folks. Okay, the correct answer here is 1 and 2 only, so A. And the reason A is the correct answer is because in case 3, you know, you have all these wires are infinitely long, right? These wires that are carrying current. And the question is the flux through the loop changing? Is the flux through this loop changing? And look, if here is a wire, right, and you have some loop here, and you move it parallel like this with some speed, isn't the magnetic field at a distance r away from this thing? Remember, the magnetic field produced by this current carrying wire has a magnitude which we found was mu0 I divided by 2 pi r, right, where r is this distance, right? Do you remember this? And the direction of the magnetic field is going in, but the point is that whatever is the flux, this magnetic field is going in, whatever is this flux, if you move this parallel to this wire, is not changing, right? On the other hand, if you move this thing away, like you are in this case, case 1, is the flux changing? Yes. What about in case 2? Yeah, in case 2 you are moving it you're moving it like this. So in that case also the flux is changing because this loop will get farther and farther away from this wire, and so the magnetic field, which depends upon r, the distance from the wire, will change, right? Does that make sense, folks? The question is the magnetic flux through that loop changing? In other words, is the total number of magnetic field lines through the loop changing? Because that's what's going to determine whether there is an induced EMF or not, right? Now what if I change this question and in the exam you were asked rank the situations according to the EMF induced from largest to smallest? What would you do in that case? Anybody? Right, it will be 1, 2, 3. Why? Because of the fact that in 1 the largest EMF is induced, because notice that not only should the flux be changing, how fast the flux is changing is important. d phi over dt, that means the rate of change of flux. And if you pull this thing like this, if the velocity with which you're pulling it is that way, you can see that that's a really fast increase compared to if you were moving it with the same speed but in a different direction like this. Do you see it's not getting farther from that as fast? And so the flux d phi over dt is not going to be as large if you're pulling it at an angle compared to if you're moving it straight away. And in this case, of course, the EMF induced is 0, so this will rank last if you had to order it from highest to lowest EMF induced. Does that make sense, folks? Any questions about this? Okay, let's move on to the next question. This one says a variable power supply is connected to a coil and an ammeter, and the time dependence of the ammeter reading is shown. A nearby coil is connected to a voltmeter, and the question is asking which one of the following graphs correctly shows the time dependence of the voltmeter reading. So basically what they are telling you is that this is the way the current is changing with time in one coil. So for example, look here, I have two coils here, okay, And suppose I change the current in one of these coils, this coil, and the change with time of the ammeter reading of this current is shown over there, the top graph. The question is, will that actually cause any change in the flux through this loop, and hence will there be any induced EMF through this loop or not? If so, then what will be the induced EMF in this loop? What will be the graph for the induced EMF in this loop, which is sitting next to this other coil? Does that make sense? Because if the current through if there is current through this coil, is there a magnetic field associated with it? Isn't there? Yes. Don't those magnetic field lines also loop through this coil if I put it next to it? They do, right? So the thing is, if you are given a graph of the current reading and how it's changing with time for this one, figure out what should be the induced EMF in this one, and look at tell me which of the graphs shows correctly the induced EMF in the second one. Okay, that's your question. You have 1 minute to answer this question. Your time starts now. Please talk to a person next to you. All right, great. So one thing that you have to understand here, first of all, is the easiest way to rule out some of the possibilities here is to see, look, if the current reading is constant here, that means the flux that is produced by the current, the flux that is produced by this current here, for the period of time the current is fixed, wouldn't the flux be constant through both loops? In that case, will there be any d phi over dt over that period of time? No. So one thing you know for sure, the EMF induced should be 0 over this time, from this time to this time. That immediately rules out C and A, right? Doesn't that rule out C and A? Is everybody with me? Because the EMF induced better be 0 when the current is not changing with time. Okay, so those two have been ruled out. Now we have this, this, and this. Notice one thing, in one case the current is increasing with time from 0 to some time t, and then after that it's actually decreasing over there, right? So one thing that you can see is that in those two cases, should the EMF induced be opposite directions? When the current is increasing or decreasing. I mean, do you remember when I was showing you those demos, whenever we did things that were opposite of each other, the current induced will be one way or the other, right? So in other words, EMF induced will be one way or the other. So in other words, one thing we can see is here, for example, look, the EMF induced here or here are the same, and it cannot be the same in, sorry, what I mean is same in same direction. They are both positive, and that cannot be, right? Do you see? Because in one case the current is increasing, in the other case current is decreasing. So these two things should have been in opposite direction. Also notice that what about between these two cases? Should the EMF induced again go to 0 in this part? But here it doesn't. Do you see this is non-zero? So this is out too. Your correct answer is this. In this case you see that these two things are in opposite directions as you would have expected, because the current in one case is increasing and the other case it's decreasing, and here it's 0 and here it's 0 as you would have expected, because the current is constant in one case and here the current is constant. Does that make sense? Is that making sense, folks? So the correct answer here is D. Any questions about this, folks? All right, let's look at another one very quickly. A current I is flowing through a conductor. What is the magnitude of the induced EMF in the wire loop of radius r moving with a velocity v parallel to the current. You are given 5 choices. Talk to a person next to you. All right, folks, the correct answer here will be? Yeah, very good. It looks like most of you got it right. The correct answer is E, because of the fact that there is no change in the flux through the loop, right? And if there's no change in the flux, there will not be any EMF induced. Is that making sense, folks? Any questions about that? Anybody? All right, then let's move on. And before we move on, one thing that I wanted to discuss with you is I wanted to make sure that everybody actually knew how to find the cross product of two vectors written in vector notation. So for example, let's try to do an example. Suppose you are told that the magnetic field is 0.5 in the I hat direction minus 0.2 in the j hat direction and 0 in the k hat direction. This times say 10 power minus 2 Tesla. This is your magnetic field. Your velocity vector, let's say, is 3 in the I hat direction minus plus 2 in the j hat direction, and let's say 0 in the k hat direction. And this is in meters per second. Let's say that the charge of the charged particle is 1.6 times 10 power minus 19 coulombs. So this might be a proton, let's say. And the question is asking, find the magnetic force. Or suppose the question is asking, find the angle between B and V. Do you think we can do these things? Okay, so how should we do this? Go ahead, please. Good. We can make use of the fact that the force on a charged particle in a magnetic field is Q V cross B. Right, here is the external magnetic field in which the charged particle is moving, and here is the velocity. So we have to take a cross product. Let's see if we know how to take the cross product, because that's basically the point. The question is, do we know how to take cross product? Because otherwise it's simple. It's 1.6 times 10 power minus 19 coulomb. Let's not even worry about the units right now. And V is this. So this is 3 I hat plus 2 j hat plus 0 k hat crossed with this, which is 0.5 in the I hat direction minus 0.2 in the j hat direction plus 0 in the k hat direction times 10 power minus 2. And the whole answer should be in what? If everything is in SI unit, which it is, charge is in coulomb, this thing is in meters per second, this thing is in Tesla, the answer for force should be in Newton. Very good. The answer here is in Newton. The question is, do I know how to find this cross this? And do you remember from high school physics, or not physics but math, that you were told how to find the cross product? So basically what you do to find cross product will be, the cross product of these two is to make a thing like this, where you write 3, 2, 0, all the components of the first vector, and then you write all the components. Wait, is this minus? No, it's I took this to be plus. These are there is a minus here. So B is 0.5 minus 0.2 and 0. And the question is, how do we find this? So remember, but by the way, is cross product going to give you a vector? Yeah, it definitely will give you a vector. That's why it's also called vector product. Sometimes cross product is also called vector product. So what will I get in the I hat direction? So you should cross out this line, and then what you'll have is this times this minus this times this. You can see that this is 0 and this is 0, right? 2 times 0 is 0, minus 0.2 times 0 is 0, so nothing is in the I hat direction, right? The second thing is put a minus sign and j hat. This time we are going to cross out everything that is, you know, in the horizontal or vertical line with j hat. So this line and this line gets crossed out, and this time again you'll do this times this minus this times this. Do you see that again gives me 0? 3 times 0 is 0, 0.5 times 0 is 0, isn't it? Okay, so this is 0 2. Then plus k hat. So this time we should cross out the row and column that correspond to k, right? And so this time what will it be? Anybody? Tell me what should be the component. Anybody? Huh? 3 times minus 0.2. Isn't that true? So that means this is going to be minus 0.6 and then minus 2 times 0.5. So that is minus 1, because 2 times 0.5 is 1. Is everybody with me? Okay, please.
Why is it minus 1?
Oh, because it's always minus for the second thing. So it's this times this minus this times this. Okay, that's the rule. The second thing is always minus. So what does it turn out to be? It's k hat minus 1 minus 0.6 is minus 1.6. So the rule for cross product is that for the middle one, for the middle thing, when you are crossing out this row and this column, you know, if you don't put that minus sign, you have to start from this side. You see, but if you always want to go criss and cross, then you have to put a minus sign over there. Okay, that's the rule for cross product. So basically what we are seeing is that we have k hat. So what do we find to be the magnetic force then? Let's write down. So the magnetic force, is everybody convinced that magnetic force is definitely in the minus k hat direction, right? It turns out to be minus k hat 1.6 times all this junk. Q was 1.6 times 10 power minus 19 coulomb times this, cross this we have already taken into account, times this thing we are left with 10 power minus 12 and this many Newton. Sorry? What is 2? Oh, sorry. This is 2. This is not 12. You know, and this minus 2 is coming from this minus 2. Right? Thank you. So the thing, so basically we find that the magnetic force then is in the minus k hat direction, and it's basically 1.6 times 1.6 times 10 power minus 21 Newton. It's very small. Right? Do you see this is very small? Do you have a feel for what is 1 Newton force? 1 Newton force, for example, if you know, doorbell, that is roughly 1 Newton force that you're applying. So this one's turning out to be 10 power minus 21 Newton. You can see how small it is, right? All right, any questions about this, folks? Okay, how do we find the angle theta? You know, one way, go ahead. Yeah, you can do it that way. That would be a fine way to do it. Or you can either use the dot product or the cross product to do it, right? Does that make sense? So for example, what he suggested is a very good way to do it. For example, so when you have B cross V, you have magnitude of V times sine theta, and that means sine theta is what? A scalar quantity, right? So if sine theta is a scalar quantity, it will be B cross V magnitude divided by magnitude of B magnitude of V. Right? Okay. So the thing is, so we could have done it this way, or we can do it this way. So let's try both ways and see if we get the right answer or not. Is everybody seeing that this shouldn't be the vector, because then there's a problem? You cannot divide a vector by a scalar and get something that is a number. That wouldn't make sense at all. So the thing is, so this will be sine theta, and magnitude of B cross V is just 1.6 times divided by magnitude of B, magnitude of V. Do you know how to find magnitude of a vector? Is that basically x square plus y square plus z square, right? So the thing is, so magnitude of B is just going to be 0.5 square plus 0.2 square, minus sign doesn't matter, plus 0 square is 0 anyway, times magnitude of V, which is 3 square plus 2 square plus 0, right? And then all you have to do is theta will be sine inverse of this number, which you can work out in your calculator. So whatever theta turns out to be, if it turns out to be 37.2 degrees, then that's what it is. Okay, let's try it this way. So this way, how will we do it? So cosine theta will be dot product of B and V. How do you, this is much easier actually. If you're asked to find the angle, it's much easier to find it using dot product, because dot products are very easy to find. Why are they easy to find? Can you just by looking at it find dot product? You don't have to go through this kind of a mess. The only reason we got something simple here is because I chose my vectors to have 0 here. You know, they didn't have any z component, but in general cross product is much more time consuming. Dot products are easy. Why? Because what is going to be I dot I? Anybody knows what is I dot I? Huh? First of all, dot product is a scalar to begin with. What is I dot I? It's 1. Why? Because this is going to be, by definition, magnitude of the first vector times magnitude of the second vector times cosine of the angle between the two, which is cosine 0 degree. Cosine 0 is 1. Magnitude of a unit vector is always 1, right? So this is 1. Okay, what is I hat dot j hat? This is going to be magnitude of I hat times magnitude of j hat times cosine of the angle between I hat and j hat, which is 90 degree, and cosine 90 is 0. And by the way, all these magnitude of the unit vectors are still 1, but the overall thing is 0. So you know that if I find B dot V, I have to do 0.5 I hat dot 3 I hat dot I hat gives me 1, I hat dot j hat gives me 0, I hat dot k hat gives me 0. So basically I have 0.5 times 3, right? So 0.5, the first thing here is 0.5 times 3. Okay. What about this thing? Do you see j dot I will be 0 also? J dot j is going to be 1. So basically we have 2 times 0.2 with a minus sign. So this is going to be minus 0.4. And j hat dot k hat is 0. Similarly with k hat, all of these are 0 anyway. This is 0. And denominator is still the same. So denominator for this is exactly the same as here, which is going to be square root of 0.5 square plus 0.2 square, 3 square plus 2 square, right? Is everybody with me? What is the numerator here? 3 times 0.5 is how much? 1.5. So this is 1.5 minus 0.4, which is 1.1. Isn't it? Okay, by the way, one good way to check whether we have messed up something or not. By the way, didn't I also miss this 10 power minus 2 here? Yeah, I did miss that 10 power minus 2. There is a 10 power minus 2 here. And didn't I also miss that 10 power minus 2 here in the denominator? Huh? In fact, I should keep the 10 power minus 2. The 10 power minus 2s will get cancelled. Here I have 10 power minus 2. You see, because you have magnitude of B in the denominator and you are actually also considering B in the numerator. So do you see this 10 power minus 2 will cancel out? What would be an easy way to check whether everything is consistent or not? Who wants to tell me? Do you know any trigonometric identities? Because here you can find cosine theta, so you can say theta is equal to cosine inverse of this mass, and that would work out fine. Or you can say sine theta is equal to sine inverse of this, it will work out fine. Another way to see is cosine square theta plus sine square theta 1 or not? If it's not, then we have made a mistake immediately, right? So one easy check for us would be to see whether cosine square theta plus sine square theta is 1 or not. So what is it equal to? For us, it's 1.1 square, 1.1 square divided by that mass, which is, how much is it? 0.25 plus 0.04 and square root of 9 plus 4, and here plus sine square theta. Sine square is 1.6 square divided by the same denominator. So this plus this is how much? 0.29 and square root of 13, right? Thank you. At least some people are paying attention. So basically we have to square this thing, so there's no square root left. Square roots are gone because of the fact that we had to square the thing. And so this is really equal to the same denominator, which is 0.29 times 13. This is the denominator, common denominator. In the numerator, you have 1.1 square plus 1.6 square, right? The question is this really 1? I know how to take, who's good at math? 11 times 11 is 121, right? That's 121. So 1.21, what is 16 times 16? Anybody? 256, good. So this is 2.56 divided by, 13 times 29. 13 times 30 will be what? 13 times 30 will be 390. So from 390, you should subtract 13. So that is, what did you say? 377, very good. So 3.77. So this is going to be 3.77 divided by 3.77, which is 1. Yoo-hoo, so we did it right? But in general, does everybody appreciate the fact that this one is a lot easier than this one? Because even if the cross product was a very complicated thing, dot product is always very easy to do. All you have to do is multiply all the things that have the same, I with I, the coefficients, j with j, and k with k, you're done. Add them up. Whereas in cross product, you could get some really complicated things if you have all the I, j, and k components be non-zero. I just chose an example where we wanted to simplify our lives, and I took something in which the k components were 0. In general, things are not going to be easy like this. But dot product can never get difficult. So I recommend that you use this method for finding angle, in general. That's much easier. Any questions, folks? But it works out fine either way anyway. Any questions about this? Okay, then let's move on to what we were talking about last time. And we were talking about motional EMF. Remember, I showed you a microscopic way of thinking about Faraday's law and Lenz's law. The context in which we considered it was this. If you remember, so the context in which we talked about it was this. We said, suppose you have a wire, and suppose there was some external magnetic field like this, right? And we said that suppose you are pulling this wire with some speed v, this is some v external, these crosses, then what is happening to the area of this loop here? The area of that loop is increasing, isn't it? Suppose if I call this thing x, do you see that x is actually increasing with time? It is increasing with time. Let's say that this length was L. Isn't x increasing? After some time you'll see x is the wire is here. After some time you'll see this is here. So isn't x increasing if you pull it with a speed v? And what we saw is that we can either think about microscopic way of thinking about this problem, in which case we said, oh, what will really happen if suppose I think about looking at this thing microscopically, looking at this wire microscopically, when there is it's being pulled at speed v, it's in an external magnetic field, charged particles inside this will feel a force v cross b, so the positive charges will feel force down, the electrons will feel a force up, right? So in this case you have positive charges accumulating here, negative charges here, and now if it's in a circuit like this, what will happen? Will the electrons actually start moving like this since they have a closed path? Yeah, so the electrons move like this, and we can say that a current is flowing this way, because current is nothing but flow of electron, but we assume that the conventional current is the opposite direction, right? So we say that a current is flowing, and what do we call this current? This is the induced current that we are talking about due to Faraday's law. Is this what you would have expected using Lenz's law? Let's think about it. Lenz's law says that the direction of induced current should be such that it always opposes the changes in the magnetic flux through the loop. In this case, do you see that the magnetic flux is actually increasing because the area is increasing as you keep moving it? So the induced current should have its magnetic field inside the loop, which should be crosses or dots? Dots. So the thing is, so this will be the B induced. That means the magnetic field due to the induced current. These crosses are B external. This is due to the external magnetic field that you have applied. And this is what's happening due to this current that is induced in this coil. If that is the B induced, is the direction of current that we drew correct? Look, if you put your thumb in the direction of current, do you see that the magnetic field inside the loop is going to come out at you? Isn't that true? So is everybody convinced that the direction of current, induced current, should be like this? Right? This is what Lenz's law predicts, and this is what we think we find when we forget about Lenz's law, say we don't know Lenz's law, but we do know that the charges in this rod will feel a force, and there will be a charge separation, and because of this charge separation and the fact that there is a closed loop, the electrons will actually start accelerating in this direction. So it all makes sense. Now we have actually thought about it at a microscopic level also, about how the electrons feel a force when you move something in a magnetic field, in an external magnetic field. Does that make sense? We also said that if you put a light bulb here in this system, in the circuit, which has a resistance R, what you will see is that there will be some power dissipated, which will be I induced square times R. But is that power dissipated something that is coming for free? Are you getting this light energy for free? No, it is not for free. Why? Because you have to do work. Whatever is this external agency, that has to do work to pull it this way, right? So actually you might have to, for example, apply a force with your hand. Now why is it that in order to move this thing at a constant velocity you have to apply a force with hand? Is there a force acting in the opposite direction? What is that force? Who wants to tell me why is it that in order to move this rod at a constant velocity you have to apply a force? What is the force that is acting in the opposite direction? Because Newton's first law says if something is moving at a constant velocity, there must not be any net force on it. So somehow if you have to apply a force F of h to keep moving it at a constant velocity v, there must be some other force that must be acting in the opposite direction. What is that? Go ahead, please. No, it's not electric, it is actually magnetic force. What magnetic force is it? Anybody remembers? Remember this. Remember that a current carrying wire feels a force, magnetic force, which is I L cross B. Right? Isn't that true? So here now, because you have induced this current, this rod is actually feeling a force, because now it has a current, this induced current in it, I induced in it. And so if I find the direction of induced current, let's put L is in the direction of current, induced current, like this, pointing down in this rod here, and cross B, this is the external magnetic field, these crosses, right? So because nothing will feel its own magnetic field, so we are not worrying about the dots because those are produced by this current itself. We are worrying about the external magnetic field, which is the external magnetic field, these crosses that you had put. So I, which is L cross B, do you see that there's a force this way? L cross B. See, my thumb is going this way. So that is the force F of B, and so the point is that that force needs to be negated by the force of the hand. As soon as you let go, for example, if you say, oh, I'm getting free electricity, I'm getting free electricity in this circuit, you know, I'm getting free power, my light bulb is lighting without me paying anything, maybe this is what I should somehow do all the time instead of paying the gas, you know, electricity company for my electricity bills. It's not going to work because as soon as you let go of this thing, what's going to happen? Now you know, there was some initial velocity that you still have when you let go, but the force, this magnetic force, is it still there? Yeah, if the force and velocity are in opposite direction, is this a situation in which this thing will slow down? Will there be a deceleration? Yes, the thing will start slowing down, and as the thing slows down, what happens to the induced current itself? That decreases. As the induced current decreases, is the force decreasing? F of B? Yes. And so slowly over time what you will see is that the thing slows down, the rod slows down, the induced current decreases, and after some time the induced current vanishes, the rod stops. Your light bulb is gone. So it's not like you're getting free lighting of your light bulb, it's really because of the work that you did, right? This external agency is pulling and doing work. So energy is always conserved in this system. It's not that we are violating the conservation of energy. People have thought about many brilliant ideas, but they're all actually wrong ideas. You know, they have come up with all sorts of interesting ways of violating conservation of energy and producing free electricity and free things. It's not possible. Conservation of energy is a fundamental principle of physics which you cannot violate, right? Energy can only be converted from one form to the other. So your energy was being converted because you were doing work into electrical energy, right, to light the light bulb. Okay, any questions about this? By the way, if I asked you in the exam, find the induced current, will you be able to find the magnitude of induced current in terms of all the things that you've been given? So let's, you know, let's do a problem. Suppose I gave you this problem and I said that you are moving this rod, the rod has a length L. So here the example said, you know, the rod's length is, let's say, 1 meter. You are told that the speed with which you're moving is, say, 10 meters per second. And the external magnetic field in which this thing is, the crosses are, has a strength of 0.5 Tesla. Okay, and it's saying that assume that the resistance of this whole circuit is R. If the resistance of this whole circuit is R, and R is equal to, let's say, 100 ohms, the question I have for you is, do you know how to find the current induced? How do you think we should do it? Any thoughts, folks? Can we use Faraday's law? Can you not? Isn't that the easy way to do it? So, for example, the way we can do it is we can say from Faraday's law, we know that induced EMF should be d phi over dt. Let's not worry about the minus sign. I'm only interested in the magnitude right now. The direction of current and stuff we already determined using Lenz's law. It turns out to be in the counterclockwise direction. So all we care about is d over dt of phi. What is the flux in this case? It's going to be magnitude of B, magnitude of A times cosine theta, right? So magnitude of B times magnitude of A. What is area vector? Is the magnitude of area vector L times, say, x? Yeah. So L times x will be the area vector. This is A. And times cosine theta. What is cosine of the angle between the magnetic field and the area vector? Look, the area vector is going to be perpendicular to the area, right? If this is the area of cross section, area vector is perpendicular to it, right? Isn't that also the direction of magnetic field? So the angle between the area vector and magnetic field is 0, and cosine 0 is 1. So this is just 1. So basically then what we have is that induced EMF is d over dt of B. By the way, is B changing or L changing? They are not, so we can take it out of the time derivative, right? Since they are constants anyway, so they turn out to be B times L, and then I have dx over dt. What is dx over dt? Very good, that's the speed, right, with which I'm pulling it. Isn't that the speed, dx over dt? So you can see that V induced then is going to be BLV. This is the speed. So then, do I know I induced? What is it, folks? Last row. If I know V induced, what is I induced? Somebody from the last row, please. Excellent. It's just V induced divided by R. And you know, so this is going to be just BLV divided by R. Right? So this is just BL, this is the speed, magnitude of velocity divided by R. So everything you have been given. BLV, R, and so you can find the answer, and since it's current, if everything is in SI unit, the current should turn out to be in amperes, right? Isn't that true? Any questions about this? Please. Well, okay, I assume that there aren't that many, there aren't many turns of this thing, so I assume that n was equal to 1. So unless I have been told that there are several turns of wire, n is equal to say 50 or 100 or whatever, in this case I assume that this was just one strand of thing and we are pulling this rod like that. It was, yeah, because the thing is, in this case you just have a rail, a thin rail on which a rod is moving. So it's not like many turns of wire there. Does that make sense? That's a good question. So n is just 1 here. Any other questions? Okay, then the first thing that we will now talk about, the new topic, would be induced electric field. So here is the thing. What we are saying is this. What we are saying is that, okay, if I bring, say for example, a magnet close or far, you can see that there is an induced EMF in this coil, and hence an induced current in the coil over the period of time that the flux is changing. Right? Now, what do you think happens if there are no coils around? You know, if I do this kind of a thing here, do you think there's anything happening here? The answer is yes. You know, because the thing is, one thing we can think about is that, so the idea that Faraday came up with is that you don't need to have a coil there. The good thing about coil is that if there is a coil, then somehow the free electrons start to feel a force due to it. But what he said is that whenever you change the magnetic field somewhere, you will induce an electric field in that region. And it is this electric field that causes these forces on these electrons. When we are saying that there is this force on the electron and somehow they start to accelerate, you know, the electrons accelerate this way and the current starts flowing this way, what Faraday is saying, hey, you know, even if that coil was not there, what you would instead get is an electric field induced in that region. Think about it. Even if nothing was there, we can still talk about an induced current, induced electric field. So let's now put this whole idea into a different form, which is a slightly different form, and that will be the idea of induced electric field. Okay, so here is the idea. So let's say that we have a coil. So this time we do have a coil. So this is a metal coil. Suppose there is an external magnetic field that is crosses. So this is B external and this is getting weaker. I want everybody to talk to a person next to them and tell me which way will be the induced current. 1 minute, everybody, and I'm going to catch one person and ask them. So the question is, there is this external magnetic field. I have a coil that is not connected to any battery, nothing, but there is a change in the magnetic flux through the loop because the magnetic field is getting weaker. The external magnetic field in which it is sitting is getting weaker. Which way is the direction of induced current? Talk to a person next to you. Use Lenz's law. Don't worry about electric field, I'll get to that. The external magnetic field. All right, somebody from the 4th row, please. Anybody has any thoughts? 4th row. Should it be clockwise or counterclockwise? 4th row. 1st row? Clockwise or counterclockwise? Go ahead, please. How many people agree counterclockwise? All right, let's think about it. So there is B external, and all that we need to worry about is inside the loop. Do you see that B external is crosses? It's getting weaker. Should the induced current produce its magnetic field that is also crosses inside the loop? Yes, because it wants to maintain a status quo. It wants to replenish what you are getting rid of by making the external field weaker. So what you will produce will be, B induced will be crosses too, and B external is also crosses. Does that make sense? And we should only be focusing on inside the loop. So if B induced is crosses, let's use our right hand rule for magnetic field. This is the thumb rule. Put our thumb in the direction of current. Do you see the magnetic field is crosses if I have the current flowing this way? Clockwise? So the correct answer is clockwise, because if the current is clockwise, then the induced magnetic field is crosses, which it should be, because we are trying to reduce the external magnetic field, and hence we are decreasing the magnetic flux, and the coil wants to maintain a status quo. It wants to replenish what you have gotten rid of. Does that make sense? Now if there is an induced current in the direction that I showed you, would it be appropriate to say that there must be some electric field pointing in that direction? Okay, there is induced current this way. That means the free electrons in this wire are feeling a force which way? Opposite, right? Free electrons are moving a force this way, aren't they? And free electrons feel a force always opposite to the direction of electric field, don't they? So it might not be such a bad thing to say, actually there is an induced electric field, E induced, that is pointing in the direction of current. And now the idea is this, that even if I didn't have this metal coil here, suppose I got rid of the metal coil. Suppose I got rid of the metal coil, there's nothing. All we have is, just some space, where there is some external magnetic field. And the question is, shouldn't, even if we don't have a wire, shouldn't there still be this induced electric field produced due to the fact that the magnetic flux is changing? Magnetic field is actually getting weaker and weaker in this region. It is true that if you bring a metal coil, because of this induced electric field, the metal coil will have electron which will feel a force, and they will start to accelerate, and you will see an induced current, something that you can measure with your ammeter. But the point is, Faraday's idea is that even if there's nothing, it's just empty space, vacuum, if you change the magnetic flux in some region here, there will be an induced electric field in that region, here in this region. And the interesting thing about this induced electric field is that it will actually form closed loops. You've never seen anything like this before, never. This looks more like what? These induced electric fields, do they remind you of something? Have you ever seen electric fields that close on themselves like this? Because you have to appreciate this is very new to you. You've never seen anything like this. In fact, electric fields always look like what? They always start at positive charges and they always end at negative charges. You never see them forming closed loops. What you do see forming closed loops are magnetic fields, for example. We did say that if you have a long straight current carrying wire, the magnetic field will form closed loops around it. So these electric fields that are induced, because I'm changing the magnetic field in this region, first of all, they form closed loops that you have never seen before. All the electric fields that we discussed in chapters 21, 22, 23, they were all starting at positive charges, ending at negative charges. Not like this. Here, look at the arrows. The arrows are always, they are going in full circles. Isn't it? Now, here is the thing. From Faraday's law, we know this. We know that the induced EMF should be equal to minus n d phi over dt. Let's not worry about n right now. Let's assume that, there's just change in the flux. So basically what we have is that induced EMF is minus d phi over dt. This is Faraday's law. But I want to be able to put this induced EMF in terms of induced electric field. Because the thing is, induced electric field will be there even if I don't have a coil. And the way to do it is, let's think about the work done. If suppose I did have some charged particle and that was moving around like this, how would I find the work done? Do you remember how to relate V to electric field? Go ahead, please.
The change in potential equals the negative integral of E back.
Very good. So the thing is, this thing is actually in E induced dot dl. Right? So basically what we see is that this is a new way of writing Faraday's law. And in fact, if you ever take an upper level E&M, either in either in upper level physics or upper level electrical engineering or chemistry or something, what you will see is that this is the form that is used more often. Because this form does not require you to have, first of all, you don't have to have a wire there. You don't have to have a loop. You're talking about just induced electric field in some region because you're changing the magnetic field in that region. So this is another way of writing it. Now notice something very important, folks. This electric field is like something that you've never seen before. I keep emphasizing this because of the fact electric force produced by charged particles is a conservative force. That means the work done only depends upon the what? Initial and final points and not on the path. Isn't that true? So in other words, if suppose I move a charged particle, there was some electric field here, I move a charged particle from here and I bring it back here, how much was the work done? 0, isn't it? If the initial and final points are the same, there is no work done by the electric field that is produced by actual charges. That is not the case here. So in this case, the electric fields are very bizarre. They are forming closed loops, and what you're finding is that integral E dot dl, which is related to the work done, will be related to minus d phi over dt. It's not 0, rather it is equal to minus d phi over dt even if these things are forming closed loops. So it is different. So the thing that I want to point out is that the electric field that is induced is not due to a conservative force, like it is for the case of electric field produced by charged particles. So this is very different kind of electric field than field produced by charged particles. Any questions about this? Okay, then the next thing, we are heading slowly towards applications of Faraday's law, application of this law, and the first thing that we will talk about will be called self-inductance and inductor. Do you know what an inductor is? Anybody knows what an inductor is? Inductor is nothing but any coil, you know, any closely wound coil, you know, a solenoid is an inductor. So basically inductor might be a very hi-fi word for just coils wound around, you know, like this. So basically a solenoid is an inductor. Now what is the meaning of self-inductance of an inductor? So here is the idea. You tell me, what do you think will happen in this situation? And I'm looking for my magnet. Oh, here is my magnet. Okay, so the thing is, we are saying that when you bring a magnet close to a coil or far away from a coil, close to a coil, far away from a coil, we are saying there's a current induced in this thing. There's a, because of the fact that there is a change in the magnetic flux, right? We don't even have to talk about this. What do you think will happen if I actually just turn on a switch and I try to pass current through some coil? If I turn on a switch and I try to pass current through a coil, so I'm connecting it to a battery and I'm trying to pass current through it, do you think there will be a change in the flux through the loop, through the wire? The truth is that if you have this situation, let me ask you this question here. So suppose here is a loop, okay, here's a battery. This is plus, this is minus, this is V. Some V battery is, let's say, 3 volts. This is the switch. At the moment I close the switch, what is the flux through the loop when the switch is open? B is equal to 0, isn't it? But as soon as I close the switch, is there going to be a current like this? Wouldn't there? Okay, and so during that short period of time when you actually made this switch close, wasn't there a change in the magnetic flux through the loop? Because initially there was no magnetic field through the loop and then there was. So do you think that over that short period of time that you're making the change, there should be an induced EMF, an induced current through this loop? Yes. This property of the coil that always opposes the change in the magnetic flux through it is called self-inductance, and it's denoted by this symbol L. Now formally we are going to define self-inductance like this. Self-inductance of a coil L like this. We are going to define it as L times I should be equal to N times phi of B. What is this? This L is the self-inductance. So that means self-inductance is N times phi B divided by I. What is N? N is the number of turns of coil, phi of B is the magnetic flux, and I is the current in the coil. Who wants to tell me what should be the SI unit of this thing called self-inductance? I don't want to hear some fancy names, just something based upon this equation that we have right in front of us. How would you define, if this is how we are defining self-inductance, what should be the SI unit of self-inductance? Anybody? Shouldn't it be the unit of flux divided by unit of current? Go ahead please.
Webers per amp.
Very good. It should be SI unit of L should be the unit of flux. Unit of flux, remember, is magnitude of B times magnitude of A times cosine theta. Cosine theta does not have a unit. Magnitude of B is Tesla. Magnitude of area is meter square divided by unit of current, which is ampere. And by the way, Tesla times meter square is given a shorter name often. People call it Weber. It doesn't really matter. So Weber is a shorter name for Tesla times meter square divided by ampere. And it turns out that this thing, Tesla meter square over ampere, or Weber divided by ampere, is given a shorter name. It's called Henry, after the scientist who did a lot of work in this area. So this is the SI unit of of self-inductance is Henry, and you can write it as H with the symbol H. Okay, so Henry is nothing fancy but Tesla meter square per ampere or Weber per ampere. Any questions about this? Okay, now I again don't want you to get fooled into thinking that the self-inductance of a coil, so this is the self-inductance of some coil. I don't want you to think that L of a coil depends upon the flux through it or depends upon the current in it. Why not? Why not? Because if you increase the current through it, what will happen to the flux, magnetic flux through it? It will increase, so that the ratio of phi over I will remain constant. I want you to be very careful, because this is exactly like this thing. Remember, in fact, in this class we are going to talk about 3 different things. We already have talked about 2 things. One of them was called resistance of a resistor, right? What was it? It was the ratio of, for ohmic material, what is R? V over I. How did we define capacitance? Q divided by V. And now we are defining something called L, which is N phi over I. It turns out that in any electronic circuit, if you look at any integrated chip, what you will see is that it has 3 major components, R, L, and C. These are the 3 things you'll find, and in fact they're so tiny, oftentimes there are billions upon billions of these things in one small chip, this big. You know, they're so tiny that you can't even see them. So the point is, you will find resistors, capacitors, and inductors with some inductance L. All right? None of these things, R, C, and L, are properties of those inductors, capacitors, and resistors. They do not depend upon, R does not depend upon V or I for an ohmic material. Capacitance does not depend upon Q or V. L does not depend upon phi or I. Why? Because if you increase voltage, current will increase such that the ratio stays constant. If you increase the voltage, total charge stored will increase on capacitor plates such that the ratio is constant. Similarly here, if you increase the current, the magnetic flux through the coil will increase such that the ratio stays constant. So it turns out R, C, and L are all properties of the capacitors, inductors, and resistors. They do not depend upon all those other external things. They only depend upon the geometry of those things. So for example, let's try to calculate the inductance of a solenoid. So let's try to calculate L for a solenoid to prove to you it won't depend upon phi or I. So calculation of L of a solenoid. And of course we are going to consider that the solenoid is infinitely long. All right. So if it's an infinitely long solenoid, that means extremely long compared to the radius of this thing, and very, very tightly wound. Do you remember from long time ago we said that the magnetic field, due to a very tightly wound infinitely long solenoid, you can find the direction of magnetic field. It's along the axial direction. If the current is flowing this way, then the magnetic field will be that way. If the current is flowing this way, you can see the magnetic field will be the other way, right? You can use your right hand rule to figure out which way the magnetic field should be, whether it should be actually this way or that way. So the magnetic field due to this solenoid obviously is either this way or the opposite, but it's definitely along the axis. And do you remember its magnitude? Who remembers the magnitude? Does it depend upon the radius of this thing? No. The only thing it depends upon was the current and the number of turns per unit length. That little n was number of turns per unit length. Do you remember that? Okay, if that is the case, let's try to figure out what is L of this solenoid. We know from the definition of L, this should be n phi over I. What is phi of this solenoid? Should it be magnitude of B times magnitude of A times cosine of the angle between B and A? By the way, what, you know, if this is, if here is a solenoid, this is a solenoid here, this red thing here, what would be the area? Area is the area of cross section, isn't it? So if this is the area of cross section, let's say one area of cross section, isn't the area vector perpendicular to that? So the thing is, so do you see the magnetic field and the area vectors are pointing in the same direction? So cosine theta is cosine 0. Basically, this is the flux phi, magnetic flux. Divide that by I. So what we have then is N times B times A divided by I. But we already know that B of a solenoid is mu 0 I times N. So this is N times mu 0 times I times N times A divided by I. Notice that I and I get cancelled, and what we are left with is L is equal to N mu 0 little n A this. By the way, do you know the relation between little n and big N? Okay, if this is the thing which is number of turns per length, this must be the total number of turns n divided by the length L. Do you see what I'm saying? Little n and big N. Big N is the total number of turns. So from here you can see that n should be equal to little n times L. L is the length of the solenoid. So then if we want to write everything in terms of little n, this will be n times L mu 0 n times A, or the inductance of the solenoid per unit length will be mu 0 n times n is n square times A. Do you see? The inductance only depends upon the length of the solenoid, the number of turns per unit length, area of cross section. It has absolutely nothing to do with phi or I, even though we started out with that expression. It only depends upon the geometrical properties. Do you see the length of the solenoid, the area of cross section, and the number of turns per unit length? They're all geometrical properties, aren't they? So is it clear that just like capacitor has its capacitance only depend upon the geometrical properties, not on the charge or the voltage, here the inductance of a solenoid does not depend upon the phi or I, the magnetic flux or current, but it's a geometrical property, depends upon N, A, and L. Any questions about this, folks? Anybody? Okay, then now we are going to talk about circuits that actually have an inductor, that means a coil, and a resistor. Remember, so far we have talked about what kind of circuits? Circuits that have resistors only, circuits that have capacitors only, and circuits that have resistors and capacitors. Isn't that true? Let's now talk about circuits that have an inductor and a what? Resistor, right. And in the end, you know what we are going to do? We are going to also talk about a circuit that has inductor and capacitor, and in the end we are going to combine the three, and we are going to talk about circuits which have resistors, capacitors, and inductors, all the three things. Okay, so that's going to be our ultimate thing, but let's get going, and we'll first talk about LR circuit. Okay, before we talk about LR circuit, which will be looking like this, you will have an inductor, you will have a resistor, and you will have a battery. Let's talk about this circuit right now, and the switch. Here is the switch. This is some battery. We will have a V battery. This resistor has resistance R, and this inductor has some inductance L. Now here is the thing. From Faraday's law, as soon as we close the switch here, what do you think will happen in inductor? I already talked to you about it. I just erased it. Remember I said to you the current will not immediately become maximum. It will gradually go to its maximum value. Why? Because the coil will see a change in its magnetic flux. Isn't that true? So this inductor or coil or solenoid, whatever you want to call it, it won't let the current go to a maximum value all of a sudden. The current will go to the maximum value as a function of time gradually. Ultimately it will become maximum value. Why? Because it will induce a magnetic field and a current, induced current in it, that will oppose the fact that as soon as you close the switch, the battery is trying to send current this way, and because of that the magnetic flux through it will increase. There will be some B external, B battery, due to battery, and this thing will oppose it. It will produce some induced current that will have its magnetic field pointing in the opposite direction, and that means the current due to that current that is trying to oppose the magnetic field produced by the battery current will be flowing in the opposite direction, and so the current will not increase to its maximum value all of a sudden. Now can we actually use Faraday's law to put all of this in a very concrete setting? We know this. We know that V induced is minus d phi over dt. Isn't this Faraday's law? Is this Faraday's law? Good. Can I write it like this? Can I put the n inside? Does it really matter if I write it like this? N times phi? Or is it okay? It's okay because n is constant anyway. If you put a constant thing inside a derivative, it doesn't do anything. You can pull it out. The only reason I'm doing it is because look how I define the inductance. Look at this. N times phi is what? L times I, isn't it? So can I, instead of that, write it like this? Can I say that this is nothing but d over dt of L times I? Is that okay? Why? Because N times phi was defined as L times I. This is how I defined L. But L is a constant for a given inductor. In fact, I showed you that L is a constant. Look, L is a constant. If L is a constant, I can pull it out, and what I find is that the induced EMF is minus L di over dt. This is the induced EMF through an inductor. So here is the thing, the job here now is to find this. You have to tell me what is the current in this circuit as a function of time. So for example, I could ask you at t equal to 3 millisecond, or t is equal to 5 millisecond, or t equal to 30 millisecond. Can you tell me how much should be the current? And no, it is not going to immediately become V divided by R. That won't happen. That will happen after some time. Remember I told you the current as a function of time will not immediately go to its maximum value. That maximum value, does everybody see that I max should definitely be V divided by V battery divided by R? That's just Ohm's law, right? Because in time after the switch is closed, the coil will stop resisting the change and it will get used to the battery current, and in that case it doesn't do anything special. It just becomes a regular coil. Is the goal clear? We are trying to find the current in this circuit, and can you see how we will find it? We are going to make use of Kirchhoff's law, Kirchhoff's voltage rule, and we will say, oh, going from A to B to C to D to A, the voltages should add up to 0, right? And for voltage across the inductor, we are going to put this. And voltage across resistor, you already know, I times R. And you know the sign. So we'll talk about it next time. Have a great day.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.